welcome to GeoHug. So I'm just promoting you up as panelists. Please don't be shy. Come on through, get the cameras on, get the mics on. Very excited. We've got Kyle Eastman with us today. But before we do get stuck into today's session, I'd like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. And yes, I am thrilled that we have Kyle Eastman joining us today. So Kyle is an economic geologist at the Montana Bureau of Mines and Geology, and it's going to be brilliant hearing from him today about critical commodity research at the Montana Bureau. At Montana Bureau, sorry, where Kyle is currently working on Montana's USGS supported Earth Mapping Resources Initiative projects with research on the critical minerals potential of the Boulder Batholith, Radersburg, Giant Hill, and Sheep Creek areas. And this is going to be a fantastic session. So I hope you all enjoy it. And yes, thank you so much, Kyle, for joining. It's awesome having you today.
Yeah, thank you. It's great to be here.
It's brilliant. Before we do get stuck in, I was really curious what got you into geology to begin with.
Ooh, well, that's a long story, but the short of it, I guess, is that I grew up as a mineral collector, and I grew up in central Arizona, just always going out on the weekends collecting rocks, and that was a fun thing that I did all the way up through high school. So when it came to choose a major in undergrad, geology was an obvious choice. Yeah.
Oh, I love that. That is brilliant. And I understand you have traveled around a fair bit. You've been in Tasmania and you grew up in Phoenix. And what have been some career highlights or travel highlights for you?
Yeah, well, I spent a season in Oregon as a park ranger at a cave.
Oh,
So that was good fun. I've also worked in the Grand Canyon region of northern Arizona doing work for the Bureau of Land Management. Some of that was cave research and mapping and general geoscience, interny kind of stuff as a young geo. And yeah, of course, I've been to lots of places in Australia, Indonesia, South America a bit. So yeah,
you've been everywhere. Awesome.
been fortunate to see some great rocks.
Yeah, that's epic. And speaking of rocks, I am curious which favorite pet rocks you've brought along for us today.
Yeah, I've got a few good ones. The first one is from Australia, and this is actually from near Hobart. And what this is a Jurassic sediment, and what makes it unusual, it's got some dog hair on it, sorry, but it is a bivalve that's been replaced with hyalite opal. So I'm not sure if you guys can see that. There's this part right here that is a little bit bubbly, and it's got clear opal there. And so that is from just outside of Hobart, believe it or not.
That's awesome.
That's
Tasmania
one of my
represent, Mark.
exactly.
Yeah, we got Tassie down represented. I love it. That's brilliant.
There it is. Got to have a shout out.
Yeah, that is awesome. Well, yeah,
I've
thank
got
you.
a few other
Oh, you've got more.
rocks too.
I love it. Bring it
I've got
on.
two more. So I've
Yes.
got a fluorite from Montana, and so we'll talk a bit more about the occurrence of this fluorite because it's kind of unusual, and pretty nice specimens, nice crystalline material there. And then the third one is a funny one. Um, Hopefully not too inappropriate, but this is a concretion from some of the sediments that we're mapping in out in on the east side of the Boulder Batholith. And it's got a magnificently tapered shape to it. So yeah, use your imagination as to what you think that looks like, but it's actually a septarian nodule. So on the back side of it, you can see that it's got sort of a fracture pattern and it's got calcite that's infilled in it there. So there it
Wow.
is. There's my poop rock, and keep that with me everywhere I go. Not really.
That is very awesome and unusual. I love that. No, this is brilliant. Thanks for sharing that with us. And yeah, thank you so much again for joining us today. It's awesome. Yeah, if you want to share your screen and we'll jump on in.
My name's Kyle. There's my contact info if you want it. You can also find it on the website for the Montana Bureau of Mines and Geology, which is where I work as a geoscience researcher. And this photo here is Butte, Montana, where the Bureau is located. We can see the historic and modern mining scenes there. The little hill there on the left with the arrow is where campus is, and that's an Eocene volcano that we'll talk a bit more about later. And then, of course, all the pits there where they mined the porphyry copper deposit. So I've got two parts to this talk where I'll kind of do an introduction to the geology of Montana and an overview of the critical commodities that we have and the opportunities to study those that we've had at the moment. Um, and then I'll do a little bit more of a deep dive, if there's time, on our Radersburg project. So without further ado, here's the breakdown of what the Montana Bureau of Mines and Geology does. We are the state survey for Montana. We do geology, and that includes geologic mapping, economic geology, geohazards. We have an environmental program that deals with mine waste and mine waste as a resource. We do all sorts of water things. That includes both the groundwater assessment program and the groundwater investigation program, which do slightly different things. And we have data that's served up on our website. We have a data preservation program that includes housing historic research collections and scanning and digitizing documents. We have an energy program, coal and petroleum. And then on our website, you can find our data center and GIS hub, as well as our publications catalog. And on campus, we have a pretty nice mineral museum, and there's an outreach component to what we do, which is, of course, what I'm doing here today. All right, so I realize that many of you might not know where Montana is. And so Montana is in the northwestern US. We share a border with Canada, as well as Idaho, Wyoming, and North and South Dakota. And if you go to our website, this is our GIS data hub. You can find all sorts of maps, geologic maps in Montana. And there's Butte, that's where I'm located, and that's our headquarters. But we also have a satellite office in Billings in the eastern part of the state, and they do more groundwater and energy resources research. We're a non-regulatory organization. We're state funded with supplemental federal dollars as well. So we get to have fun and just do research. So in the next few slides, I'll just go through and describe the geology in Montana and the critical commodities that we have in different parts of Montana. So starting with the old rocks and then working our way younger, we have a number of Archean crustal provinces, including the Wyoming province, the Medicine Hat province, and then there's a structure in between that some folks refer to as the Great Falls Tectonic Zone. There you can see, based on the colored little blobs here, there's not actually a huge amount of outcrop. So some of this is inferred with regional geophysics. And there's a bit of debate as to whether or not this Great Falls Tectonic Zone is an actual thing. But regardless, we have in the southwestern part of the state a number of really interesting exposures of Archean rocks. And that includes the Stillwater Complex, which is a 2.7 billion year old layered mafic intrusion and holds resources for platinum group elements and a handful of other metals. And that's what this thing looks like. And so, believe it or not, this is not a sedimentary rock that's been turned up on end, but this is a layered mafic intrusion. And what you're seeing here are banded plagioclase and orthoenclinopyroxenes. So really incredible exposures. I believe this specific outcrop is listed somewhere on the UNESCO World Heritage Site or something like that. It's a pretty special outcrop. And this is what the JM reef looks like. So this is the platinum and palladium bearing reef that's in the Stillwater Complex. It's tilted up on end, just like in the previous images there. You guys think you'd recognize this if you were out in the field and stumbled across these rusty colored rocks? I like to think that I would, but maybe I wouldn't. But that's the thing. That's it right there. Platinum and palladium in there, little bits of sulfides, just making it a bit rusty. Okay, so working our way younger, we have the Belt Supergroup, and this was a pretty good sized basin that filled up with sediments during the Mesoproterozoic. And some of you who have worked in Australia, Tasmania, you might be familiar with the Belt Basin because there's some similar rocks down in that part of the world. And so you can see the paleogeographic reconstruction there, putting the Belt Basin somewhere near, there's a little Tasmania question mark right over there in this figure. And so maybe there's some similar rocks in this part of the world, which is kind of cool to think about. But these things host sediment-hosted lead zinc deposits, some copper and some silver as well. And so this has a pretty profound impact on the geology of Montana. If any of you've seen photos of Glacier National Park, if you've been to Glacier National Park, these are the kinds of rocks that you see there. Okay, we're just kind of quickly going forward all the way to the Phosphoria Formation, and fast forwarding over 1 billion years. And the Phosphoria Formation was this inland sea that created, as you might suspect, some phosphates, but also scavenged some rare earth elements, and there's a bit of vanadium and maybe a bit of chromium in these things. And so the majority of the Phosphoria is actually down in Idaho and Utah, excuse me, but is actually a bit of it in southwestern Montana, and it's being studied by the Bureau as a potential source of rare earth elements. And for much of the Mesozoic, this is what North America would have looked like. You can see Montana there in the center, roughly, would have had some mountains and would have had some inland seas. And so during the late Cretaceous, this was a really interesting time. And we see a lot of rocks here that represent this transition from a sort of inland sea to a more terrestrial environment, to volcanoes erupting into that inland sea, and then ultimately emplacement of our batholiths. And so that kind of looks like this. So after that inland sea is sort of drying up and receding, we're seeing these Elkhorn Mountain volcanics here. This is late Cretaceous, about 90 to 80 million years. And then around 75, we have the emplacement of the Boulder Batholith, which is a big granitic batholith that's associated with a lot of our ore deposits in southwestern Montana. And all of these igneous rocks that I'm now talking about are part of this Jurassic to Eocene magmatic arc that extends from Alaska all the way down to Mexico and potentially beyond. All right, so this Boulder Batholith, how did this thing form? And a lot of folks suspect that what's happened is this batholith has been emplaced along thrust ramps. And so here's the kind of schematic on the right of how this might have allowed melt to move up the thrust ramp and accumulate in this thrust sheet, and then it's been eroded down. So we see the fold and thrust belt here with the batholith kind of sitting in the middle of it. So it's an interesting environment, geologically complex. The story is not done yet. And the Boulder Batholith, of course, is one of the most significant concentrations of historically mined sites in Montana. So, of course, it was a natural choice to go and study critical commodities. There's a variety of different deposit types that are present. We have pegmatites that are associated with the Boulder Batholith that typically only have minor rare earth element content. They're not the interesting pegmatites, unless you're a mineral collector like me. We have, of course, proximal magmatic hydrothermal flavors, including porphyry and epithermal deposits, these polymetallic systems. And all the elements in red there are all the potential critical elements that are on the USGS list that are of concern for the US at the moment. We also have proximal contact metasomatism in the form of skarns. Typically, these are copper gold skarns around the Boulder Batholith, but we do have tungsten skarns in some other locations. So we see some variation there. And then we have distal carbonate replacement deposits, and those things are typically lead, zinc, silver. They occasionally have barium, supergene, vanadium, and molybdenum. So these are the sort of flavors that we're seeing. And there's Butte right there as an enormous cluster of historic mines on the map. And from a periodic table perspective, these are the elements that we're seeing that are probably most likely to be of interest in terms of critical commodities in Montana. And the red ones, of course, are Boulder Batholith. So we see some elements on the right there that are associated with zinc, and those would be the elements that are substituting into sphalerite, such as gallium, indium, germanium. But also we see other chalcophile elements there. Bismuth and tellurium are occurring at some gold deposits in the Boulder Batholith region. We also have manganese in polymetallic veins, tungsten in skarns, and vanadium and barium, as I mentioned. So putting that all together, so far we can see we have this Archean rock is green in the southern part of the state. We have this belt supergroup, enormous sedimentary basin, in some cases up to 20 or 25 kilometers in thickness. So enormously thick sedimentary basin there. And then we have volcanic rocks and the Boulder batholith. So really Butte is situated kind of in a very complex, diverse part of Montana. So there's Butte. This is the sort of the satellite imagery of what we just saw in the intro slide that I had. So there's the Berkeley Pit, which is a flooded historic porphyry copper mine. Continental Pit to the east there is actively mined. That's the Yankee Doodle tailings impoundment. To the north there, and of course we're on the campus of Montana Tech. That's the blue star. And the history of mining in Butte is really interesting, and that history is very vibrant and celebrated today. We have all sorts of music festivals, and really we enjoy this historic aspect of living in the richest hill on earth, so they say. And this here is the Irish Festival, and they used one of the old head frames as a main stage for this festival. So Butte likes to do this sort of thing and have a lot of fun. So the history of Butte is lots of polymetallic veins that were initially mined. They initially found gold placers, chased those up to silver veins, mined the silver veins, and then around the turn of the century, copper started becoming important for the electrification of the nation. So all those red veins in the center there are all the copper-rich veins. And so that's where the Berkeley Pit went in. And then they found the big porphyry domes at depth, and the rest, as they say, is history. So it really is an important deposit for the history of the U.S. And in the early 1900s was probably responsible for producing, somewhere between a third to half of all the porphyry or all the copper produced in the world. So enormous copper producer that really helped with World War I and World War II efforts. All right, so moving on from Butte, which was in the Boulder batholith around 60 million years, we also have this central Montana alkalic province and some rare earth element bearing carbonatites, which is very interesting. So we have these unusual flavors of melts that are coming up through sporadically in central Montana and also in western Montana. So here's an example of a carbonatite from the Sheep Creek district, which is along the Montana-Idaho border. And this is one of our USGS funded projects that we're working on. And so here on the right, you can see that there's a carbonatite sample with bastnasite, ansilite, and alunite, so mixtures of rare earth bearing carbonates and silicate minerals. Progressively moving younger, we have some volcanic rocks that erupted over the top of the Boulder batholith and those Elkhorn Mountain volcanics that I described earlier. And so these are the Lowland Creek volcanics. They have epithermal gold deposits. And so here's an early paper by Dick Silito describing a diatreme-hosted gold deposit at Montana Tunnels, which is right here. This is a really interesting one. Fascinating, cool paper in 1985 that Dick Silito put out describing the breccias and the mineralogy of this deposit. Also associated with our Eocene volcanics are sapphires. And so there's a few places in Montana where you can actually see the dikes that brought the sapphires up from depth. And the Yogo mine is one of those. So that's the image on the right, is a sapphire actually hosted in the dike rock. And it's one of these unusual alkalic compositions. And then we find alluvial sapphires all over southwestern Montana, well, in certain gravels. And those historically were used for watch bearings and now are mined for gemstone material. Okay, so moving progressively younger, you'll notice that there's some linear mountain ranges in Idaho, and some of those sorts of linear mountain ranges extend up into Montana. And sure enough, we have basin and range style extensional tectonics that extends just into southwestern Montana. So in addition to this laramide orogeny where we had compression, we had a fold and thrust belt, we had emplacement of the Boulder batholith, then we go and we rip the carpet out from underneath it and we do extensional tectonics, overprinting all of that. So it really complicates the story yet again. And so here's an example of that extensional tectonics in the form of the anaconda detachment. And so this here is Butte on the figure to the left. And in this cross section, you can see how the boulder batholith slid off of the rocks below it off to the in an easterly direction. And there's a whole bunch of mylonites that are exposed along what's called the anaconda detachment there. And in those mylonites, in some of the disturbed rocks right there at the attachment are these fluorite occurrences. So that's pretty interesting, and that's something that we're doing a little bit of work on right now. Okay, so the last chapter in the geology of Montana is the movement of the Yellowstone hotspot. And so 16 or so million years ago, you had these calderas. They're working their way across. One of the older ones is McDermott caldera, which you might be familiar with as a lithium resource. And so working their way younger, you can see that that's dramatically influenced the geology and the topography of the region. And all the red dots are earthquakes as well. So it's impacted what we call the intermountain seismic belt, which extends from down in Utah up in towards Canada. All right. So at this point, I'll tell you a little bit more about our team and our research projects and the new data types. So that was kind of a whirlwind tour of the deposit types that we see in Montana, the rock types, where they are, and how they got there. So our team at the moment, and this is a growing team for sure. We have Adrian, Jared, myself, and Ryan. Adrian's working on rare earth elements in the Phosphoria Formation. He's an expert on carbonatites, and he's also working on critical minerals and mine waste. Jared did a PhD on Yellowstone, so he's an expert on epithermal systems and hydrothermal alteration mineralogy. I'm working on the boulder batholith. I've worked on porphyry and epithermal and skarn deposits, but also supergene mineralogy. And Ryan Davison is working on a project right now to study rare earth elements in coal and fly ash. And we have some students, and we'll talk a little bit about some of those student projects. All right. So our two main external funding sources are both coming from the U.S. government. And one of those is from the Department of Defense, and that's the Army Research Laboratory project that we have going on. And the Army Research Lab is having us do these regional assessments. They're really focused on specifically rare earth elements and a handful of other elements. And they're supporting regional looks at processing and evaluating historic mine sites. And so there's a number of Army Research Lab tasks that sort of span both the Montana Bureau of Mines and Geology as well as Montana Tech. And those support a couple master's student projects. We have Everett Labuda working on the boulder porphyry. We have Nick Reisdorf working on rare earth elements in the Phosphoria Formation. And the project that I'm mostly involved in is the USGS Earth Mapping Resources Initiative, or Earth MRI, as we call it. And there's a whole bunch of different tasks involved in there. We do data preservation of historic collections. We do geologic mapping and geochemistry. And so my primary project is that Radersburg project, but also I'll be working on a basin project going forward, and we'll see those on a map here shortly. The Earth MRI project is also funding work on the Phosphoria and getting some really incredible geophysical data that I'll show you a little teaser of in a minute. We have some external collaborators in academia, in the government world. We have some industry collaborators, and John Dillis, believe it or not, is working as a contract mapper with us. So we enjoy getting out in the field with him. All right, for this Earth Mapping Resources Initiative, we're doing geophysical surveys, and we covered the eastern half of the boulder batholith with airborne radiometrics and magnetics in 2022. And then we flew what we called the Butte extension of that in 2023. We're also flying some areas around those rare earth element bearing carbonatites in the Sheep Creek district. And we're continuing to infill what we call the Montana-Idaho porphyry belt. So we'll hopefully have a whole swath of high resolution airborne geophysics that goes from central Montana down to the southwest into central Idaho in a number of years. So hopefully by 2026, a lot of that will be flown. And so we're chasing up these airborne geophysical surveys with mapping and geochemistry. And this Radersburg project is my primary project at the moment. There's porphyry, epithermal, skarn, and carbonate replacement deposit types there. And then we have a number of other mapping projects that are in various stages. We also have, mine waste. Waste is a resource project that is being supported by the USGS, and data preservation, which also, in addition to scanning maps and documents, gets us whole rock geochemistry on historic sample collections, which really boost what we're doing in some of these historically mined areas. And there's the helicopter down there with the magnetic instrument on the stinger sticking out in the front, and then the radiometrics is sitting in there in the back seat, the gamma ray spectrometers. Okay, so you can go and download the 2022 data from the USGS website. You can do that right now if you wanted to. And that's what it looks like. So the magnetic data there and the radiometric data. There's also there's a combination. When you download the data, you get process TIFFs that you can just drag into Google Earth or ArcGIS or whatever you want to do. But those of you who are power users and want the raw data, that is out there as well. And what's coming? So here we have our 2024-2025 survey polygon, which is enormous. This is going to be keeping the contractors busy for the next couple of years. And we're doing 200-meter flight lines east-west, and then 2-kilometer tie lines north-south for this entire area. So like I said, we'll have a pretty impressive swath, I think, pretty impressive swath from the northeast to the southwest across the Montana-Idaho border. All right. Radersburg and Giant Hill quads. These are both 7.5-minute quads that we're mapping at the 1 to 24,000 scale. And these are 3-year projects. So we're about halfway through the projects. There's porphyry epithermal deposit types, there's skarns, there's carbonate replacement deposits. And this area is on the eastern side of the Boulder Batholith. So it's really interesting. And there's a number of magma blobs that came up and solidified in the Paleozoic to Mesozoic sedimentary sequence, but also the Elkhorn Mountain volcanics. So we have a great diversity of rock types and deposit types to work on in this area. And on the right, there's a nice sample of the Diamond Hill porphyry with quartz stockwork veining, bit of magnetite, pyrite, chalcopyrite in there. All right. Because this is USGS funded work, here's a disclaimer. Don't chase us down if you go drill a hole out there and you don't find a porphyry. So not my fault, not the USGS's fault. All right. So quick overview of the geology in Radersburg, which is a lot like what you just heard in the first part of the presentation today. It's within the Helena embayment of the belt supergroup. So we're within the Laramide fold and thrust belt, where the belt supergroup is down there at depth, but we're seeing mostly the Paleozoic and Mesozoic sequence, and then overlying Elkhorn Mountain volcanics, and then intrusions that have also been related to this Laramide orogeny. And a lot of the mineralization is coming in with those intrusions. That's our magmatic hydrothermal environment that we'll see in this region. We have some younger tertiary volcanics. We have basin range extension that complicates the story a bit. And then we have superficial weathering processes. All right, so here's our mineralization. We have porphyry, copper, gold, moly deposit types. And I'll talk a little bit about this Diamond Hill porphyry because it's got great textures and gosh, it's exposed along as a road cut. So it doesn't really get much better than that. We have gold-bearing pyrite in vein systems, some of which are pretty extensive and can be traced back to our porphyry systems, and so they're thought to be related. We have copper gold skarns, plus or minus a bit of bismuth and tungsten, but these skarns here are a little bit more oxidized flavor, and so they're not carrying as much tungsten and moly as some of the skarns that we see in other parts of the state. We also have lead, zinc, silver, carbonate replacement deposits. Some of those are pretty good sized. And so we've got really a variety of these magmatic hydrothermal deposit types in this area to study. Here's an overview of the geology and the two quads that we're interested in mapping here. So the big red blob on the left side of the screen, that's the boulder batholith, and the main body of that is what we call the butte granite. You can see all the folded sediments. The Devil's Fence anticline is there in the center, and that has those belt supergroup rocks in the center that are then progressively overlain by the Paleozoic and Mesozoic sediments. So over here in Radersburg and Giant Hill, we actually have a syncline where the rocks go down and come back up on the east side, and that syncline is full of Elkhorn Mountain volcanics and shallow intrusions that are related to those volcanics. So it's a great place to go looking for concealed ore deposits. There's historic mapping that's been done in the region. This Klepper mapping was published in 1971, but a lot of the actual mapping was done in the 40s, and it's actually pretty darn good mapping. They certainly, in a lot of cases, knew what they were looking at, and that's what this historic mapping looks like. And so we're going through and we're remapping a lot of this. Some of it's correct, some of it isn't, but we're adding geochemical data, we're adding geochronology, and we're really drilling into the details of the mineralogy of these ore deposits in these quads. So we'll hopefully have two nice new quad maps in about a year and a half and a whole bunch of geochemistry data and geochronology data to accompany those quad maps. All right, so I talked a little bit about the Elkhorn Mountain volcanics, but these are the Cretaceous volcanic clastic sediments that immediately predate the Elkhorn Mountain volcanics. We have the Slim Sam and Colorado formations, which have sort of regional equivalents that go by a number of names in the region. But they're real dirty sediments full of like proximal broken plage and lithics, and in some cases actually heavy mineral sandstones and paleoplacers. And so this Slim Sam formation, this pre-volcanic volcaniclastic stuff that's thought to be weathering off of an island arc to the west, this stuff has a distinctive geophysical signature. So we see there in our airborne radiometrics that it's got a blue color, the Slim Sam formation, indicating it has relatively elevated thorium and uranium relative to the volcanic rocks, which are the red blobs here. Volcanic rocks or intrusions have a little bit more potassium in this case, and so those stand out relative to the volcaniclastics. So really great mapping tool to have for this region. And we did some automated mineralogy on these heavy mineral sands, these paleoplacer environments in the Slim Sam formation. Sure enough, they're loaded with magnetite. We knew that already. Bit of quartz, but also some rare earth element flavors. Nothing economic yet, but certainly interesting. And possibly, some of the mineralogy here is responsible for the radiometric signals that we're seeing. Here's some textures just for those of you who like volcanic rocks. I'm sure there's at least a couple of you out there in the audience. We see lots of breccias, lots of great breccias in the Elkhorn Mountain volcanics. We see lavas. That's the sample there in center bottom there. Pyroxene and plage, pyrrhic lava. Lots of epidote alteration. Lots of hematite as well. Here's a ignimbrite sort of top center there. Where's some compaction foliation happening there and some fiame. So these are the host rocks for a lot of our deposits, and lots of work to potentially be done in the green rock environment in navigating that space towards our deposits. Lots of epidote, lots of chlorite, bits of specular hematite, bits of calcite. Those sorts of alteration flavors are present. And so the Diamond Hill porphyry intruded into those Elkhorn Mountain volcanics, and believe it or not, it made a skarn and a porphyry in the same area. So here's some of those porphyry samples. There's quartz stockwork veining, like I showed you earlier. There's actually myrolitic cavities with disseminated sulfides, and so we'll take a closer look at those in a second. And here's the intrusive contact between the Diamond Hill stock and the Elkhorn Mountain volcanics, and you can see how really irregular that contact is, which is pretty cool. I was very excited when we found this rock. And then even better yet, there's the cross-cutting relationships of this quartz pyrite vein that crosses the contact. So this is one of my favorite rocks so far from our sampling out there. And we took some of these samples down to the Colorado School of Mines and we scanned them with a hyperspectral scanner that they have down there. Um, Looks like this intrusion has this porphyry has plenty of sericitic alteration. It's just lit up with muscovite, but there's also a bit of epidote and chlorite around it. That epidote and chlorite extends out into the Elkhorn Mountain volcanics from that contact. So it's probably pretty hornfels contact there, but still a bit of epidote and chlorite. And so let's take a closer look at that myrolitic cavity because I think this thing is just too cool. You can see that there's the, you know, really sort of crowded porphyry here, lots of plagioclase, there's disseminated sulfides, there's some mafic sites. Some of those mafic sites maybe have had a hard time. There's actually a bit of sulfide in that myrolitic cavity there, some pyrite and some chalcopyrite. And we did automated mineralogy with our SEM on that one as well. So this is pretty cool. And then what you can see is that as the porphyry was quenching and releasing its hydrothermal fluid and creating these myrolitic gas bubbles, you have crystallization of plagioclase, feldspar, and quartz as the ground mass between all of these plagioclase feldspars, which you can see on the right. So it looks like the potassium is heading in towards the center, crystallizing towards the center until eventually you get some chunky K spars and some quartz crystals, and then you have a gas bubble, and then there's some sulfides that occupied that open space. So this to me is a porphyry that is caught in the act. Like this is just fascinating to see these textures preserved, and it's caught in the act of exolving its volatiles and making an ore deposit. All right, so stepping back to our airborne radiometrics again, we can see there's Diamond Hill. Diamond Hill is right there. It's got a red blob. Sure enough, it's a bit potassic. We have this Ohio Keating area here. We have Elkhorn, which is a porphyry stock there that is right on the edge of the batholith. It's lit up with a potassic signature. And then also Montana Tunnels, which I mentioned earlier, has a bit of a potassic signature. So these are where we can start to relate our alteration and our deposit types to our airborne radiometrics. And really, we're going to be tuned on this data for probably decades to come. There's so much to unpack and so much work to be done in evaluating the mineralogical reasons for those geophysical signals. And so really to summarize all of that, we can use the radiometric data and compare it with what we see at the hand sample and at the thin section scale. And we see certainly plenty of potassium moving around in the form of hydrothermal K-spar and white micas, but also useful for some of our volcaniclastic sediments and correlating those where we can see elevated uranium and thorium. We have pretty extensive epidote chloride alteration in the Elkhorn Mountain volcanics. We have plenty of magnetite around, so we also have magnetic layers that we're using. So that's pretty complex in some areas, but in other areas it's a dead ringer of, where the magnetite is. And then the critical commodities potential for the Radersburg and Giant Hill quads includes a lot of the elements that I already mentioned, so chalcophile elements, but also elements like tungsten, vanadium, and barium. All right, so some acknowledgments here, lots of help from other folks at the Bureau and at Montana Tech. Of course, we have an Oregon State University crew who comes out and maps with us. We have USGS folks who come out and do geophysical ground truthing and geochronology and paleomag studies, that sort of thing. We collaborate with the Oregon Survey and Colorado School of Mines as well. And just to wrap things up here, here's a shameless plug for a Butte field trip that's happening next year in August. And so that is going to be a pre-conference field trip. You'll see the Butte porphyry. You'll see some of these deposits that I mentioned. Montana Tunnels is one of them. And so if you think you're going to this SGA biennial meeting in Golden, Colorado, make sure to sign up for the Butte porphyry system field trip that's going to happen as a pre-conference trip. All right. So thank you. That's what I've got.
That was brilliant. Thank you, Kyle. Really, really appreciate you doing that. Thank you.